Ken Duffy from the Hamilton Institute in Ireland will tell us all about brute force searching, the typical set and guesswork. Great.
Thank you, Sean. So, I'd like to start by establishing my credentials for coming to this meeting. Right? Seeing it's the subtext of the meeting, right, is that we're all mates of Sean's, or we're all his admirers, one or the other, right? And, in my case, both, for certain, right? So I have done some work with Sean. I'm not going to talk about it today. And in fact, this is a picture of Sean in my office, where he posted this on the internet, and so concerned was he that someone would steal this equation, he cropped it out of the image before he put it on the web. I'm reinstalling it. We can't even get people to read the paper, let alone steal the equation. So I'm going to start with that. I'm also going to start with kind of an apology. And the apology is that 95% of the time, if you hear me talking these days, I'll be talking about biology, because it's really what I'm investing a huge amount of my efforts in. Largely with my old friend Phil Hodgkin, who's the head of the immunology division in Medical Research Institute. Need to talk louder? Oh my God. My voice will get about halfway through. My old friend Phil Hodgkin, who runs the immunology division in a very famous medical research institute in Australia, in Melbourne. This work is really fun, and I think you would enjoy it if I had time to talk about it, but I'm not going to. But I'm going to hint at what we're doing. I'm going to run that film in the background. What we're trying to do is trying to figure out how cells make decisions. Right? You have this huge number of cellular systems in your body. They make fate decisions. They change their types. The adaptive immune response, which is something that all jawed vertebrates have, is a particularly beautiful example of it, where when you undergo an infection, you generate this army of cells that take on different functions and different roles. And the historical kind of biological viewpoint is largely deterministic, and often the noise is seen and heterogeneity is seen as being a flaw or error. And as you can imagine, being a probabilist, the way we tackle most of this stuff is with the assumption that this stochasticity or heterogeneity is actually being exploited rather than being a flaw of the system. I'm also going to mention in passing, because next time I come through, I promise I'll speak about this, which is work that I'm doing with Layla, who's in the National Cancer Institute in Holland, where hematopoiesis, which is another beautiful cellular system where loads of decision making goes on. So people, if they have cancer and you give them an extreme form of chemotherapy, what you do is you wipe out all of their proliferating cell systems. You give them a bone marrow transplant, because in their bone marrow they have these stem cells that can reconstruct their entire blood system, including all your immune system and everything. But when you give someone a bone marrow transplant, you know that you give them hundreds of these stem cells, but you don't know whether one stem cell reconstitutes everything, or whether they're already pre-primed to do different things or whatever. And so these people in the Netherlands have this amazing technique called cellular barcoding, where you take a virus that exists in nature, and what that virus would normally do is it integrates itself into your genome. So it's a bit like HIV is an example of one of these viruses. The retrovirus gets into a cell and then takes its own DNA and inserts it into the cell. And now every copy of that cell from there on in is going to have the DNA of the virus in it. So we take one of those viruses and we strip out its DNA, and from an information theory point of view, you'll like this because there's only one paper on it. What they do is they take a bit of DNA that we've constructed and we know in advance, and we put that into the virus, so that when the virus infects one of these cells, it inserts a little bit of barcode, a little bit of DNA that you've designed into that cell. And what happens is every progeny in that cell, we can tell that where it came from, because that has this little cellular barcode that we put in. And there's only, just to mention in passing, there is only one paper talking about how you should best design those barcodes. The ones we're using were, like Tom's lab, where Layla works, was like the first lab in the world to get this stuff really working. And they are the little snippets of DNA were built using a random process effectively about a decade ago. So they're not well designed, but there is a design problem in there. But I'm not going to talk about any of that. Next time maybe. And instead, what I am going to talk about, if I can get on to the next slide, is work I've been doing that started with a student of mine, Mark Christensen, and due to some serendipity of being friends with Muriel and her student Flavio, has taken on a kind of a different twist. I'm going to talk about this today, and the reason is I don't often get an opportunity to speak in front of information theorists, so I'd kind of like feedback on it. The other thing is there are only about 20 or 30 papers on the subject that I'm going to talk about, and 3 or 4 of them were written by this man. So Rajesh here at the front wrote some of the really nice papers on these things, so I just couldn't pass up the opportunity to speak on it. I should explain as well, the stuff I'm doing on biology, it's really driven by the biology. I'm not doing math for the sake of it. I use whatever I need for the work that we're doing. And so this project started out as an attempt to keep my mental yoga working. So the way I started this was merely as a mathematical exercise, and it's only through the good fortune of knowing Muriel that it's turned out to be perhaps a little bit more relevant than I thought. Okay. And because it's such because the literature is not fast, I hope I'll give you a reasonable introduction to the subject. So it's basically the subjects on the muddy waters between information theory and security. One of the things that you commonly see in security is a notion of complexity in security, right? That Sean takes a secret, say it's a password for his system, and if he picks it from a big list, then I have trouble accessing his system, because to get to it, I have to guess a huge number of things before I will hit upon the solution. And normally, people say something is computationally secure if they think it's going to take me a long time to find that. If the list that Sean could have picked these passwords from is very, very big, right? There's no probability usually in this when people talk about it. If there is, the way you would think of it is probably he was picking uniformly from a full list, right? But of course, Sean is more likely to have a password that says, "I love coffee," than "I love the tea party," right? So, if an attacker knows some probabilistic information about the nature of how passwords are selected, they're probably going to exploit it, right? So we're going to try and look at some of these notions of computational security, but adding a probabilistic flavor. So the first half of the talk is kind of, or in fact the first 3/4 of the talk will kind of be about that. What can we say about that? And the second part of it will be, Kai-Lai Chung said there is only one theorem in your field. You know, the asymptotic equipartition property, that's it. Which has always made me wonder what you guys do. Yeah, he has that in an introduction to his book. But so the thing is, this original premise about it being very hard to guess Sean's password if he was picking it uniformly, well, maybe I can just appeal to the AEP, right? So if all of the probabilities contained in a typical set, then the asymptotic equipartition probability tells me that nearly everything in there is equally likely, and therefore maybe making this uniform assumption is reasonable. And the only reason I thought about this was we're doing something else with Flavio and Muriel, and one of the premises was we looked at the uniform distribution. I asked Muriel, why are we looking at the uniform distribution? She said, well, probably the AEP saves us, and may as well, we're looking at list decoding. We're assuming that we're only coding things in the typical set, so we may as well assume things are uniformly distributed. So we went about trying to establish that that was a reasonable thing to do, that there was an equivalence, and the answer at the end will be that there isn't. You shouldn't be assuming that things, just because things live in the typical set, in the context of what I'm going to speak about, that's not making a uniform ansatz is an error as a consequence. Okay. So, like any work that you do, you should take it very seriously. So I'm going to start with an XKCD comic, which I'd like you to read. Susan Holmes, the bioinformatician from Stanford, suggested I use this in talks, by the way.
I think I've seen it in David Aldous'
Does David Aldous use it as well?
description of good passwords and bad passwords.
Oh, okay. So in particular, so it's a common phenomenology we all know, right, where bloody password systems make you pick awful, ensure that you have 6 strange characters and whatever in your password. But the real thing I want to emphasize in this is not so much the joke, but you're all information theorists, right? Implicit in this is kind of, if the Shannon entropy of the distribution is large, then a password is hard to guess. Right? Shannon entropy is usually a measure of randomness. So the question is that a reasonable thing? What do you believe? I know what you believe, so Tara, what do you believe? Do you think Shannon entropy is a good measure of how hard it is to guess things? You're thinking I'm not going to be speaking here if that was the case, right? So this is a question that James Massey addressed. I don't expect you to read this paper. The reason I'm putting it up is because this is the full extent of the paper. In 1994, in a lovely little piece called Guessing and Entropy, right? Where he asked exactly that question. Is there a relationship between the Shannon entropy, say, of how Sean has selected his, so we assume Sean has selected his password from a distribution, and does the Shannon entropy of that distribution tell me something about how hard it is to guess his password? So let me formalize that for you a little. Already we're going to get to a culture clash. Not just that I have a funny Irish accent, but also I'm a naturalist, which is not to be confused with a naturist, in that all of my logs will be base E, right? So I'll have e to the, and I'll have log. You can convert them to 2s if you wish, you strange people. So Sean picks a word from, and the W1 is going to hint at some stage I'm going to introduce words with more than a single list. I'm going to have words of a length of characters. And we have a Shannon entropy. So how would I guess, if I was trying to guess Sean's password, and I knew something about the distribution from how he picked it, how would I do so? And what I would do, for example, is I would order his passwords from the most likely one that he would pick down to the least likely. And then I'd guess them in turn, right? You'd start with the most likely, and you guess them down to the least likely. And I happen to be fortunate here, and somehow my first letter is the most likely one, and the last letter is the least likely one. So I guess them in order, and then a reasonable measure of how hard it is to guess Sean's password will be the expected value of how many guesses I have to make before I hit the right answer. Right? So all the randomness is in W1, it's in how that password is selected, and then I'm asking what's the average number of guesses I have to guess before I get to that W1. Okay. And what Jim said was, is there a relationship between this and Shannon entropy? And basically it turns out that there's a lousy lower bound, and it really is a lousy lower bound. If you assume that the password distribution was uniform, this is a massive underestimate, and there's no simple upper bound, right? So that in some sense Shannon entropy is not capturing how hard it is to guess this password. Okay? People still with me? All right. So that's kind of where the subject should end. Right? There's Shannon entropy has no role. But another interesting character said, okay, if we're going to study this more fully, we're going to have to introduce some regularity, right? I can't just have passwords from a single list. I need to do something to my measures to give them some smoothness. So Arikan, in a couple of years after Massey's paper, wrote a much longer one where he introduced an asymptotic regime, right? And the asymptotic regime was that he's going to have a sequence of passwords, if you like, of length k, made up of IID letters. And there's an abuse of notation here. My G is my function that maps my word to when I shall guess it. But of course, really, I have a sequence of functions because for each k, I need another function, right? It's going to order them from most likely to least likely. And I don't care about breaking ties. If 2 words are equally likely, I don't care about the order in which I'm going to guess them. And so let's study this asymptotic regime. I'm going to remind you of something that everybody in here, I'm sure, knows, which is the definition of Riemann entropy. Again, I'm going to put a 1 on it because everything is IID, so unsurprisingly it's only going to matter about the behavior of this single distribution. And perhaps the surprising result is, the number of things that I have to guess is growing exponentially. And what Arkan proved was that if you take this guesswork distribution and you take some moment of it, so you give me an alpha bigger than 0, alpha is 1 is the mean, for example, then what he's saying is these moments are growing exponentially, and the exponential rate at which they're growing depends upon the Riemann entropy, where I'm treating the Riemann entropy as a function of the parameter in the Riemann entropy. Okay. And in particular, for example, if you put in alpha equals 1, which is kind of the original question Marcy was asking about, what you find is that the average number of guesses that you're making is growing exponentially with Riemann entropy where you put in a parameter a half, right? So, most of us have a feeling for what Riemann entropies mean. If I look at it when beta tends towards 1, I get Shannon entropy. When beta tends off towards infinity, I recover min entropy. I get something about the most likely thing to happen in my alphabet. When beta goes down to 0, I'm counting the number of events with positive probability. I don't know if anybody has any intuition for what beta equals a half tells you, right?
Yeah, it's very useful. Elegant distance, elegant metrics are exactly for alpha equals 1.5.
Right. Yeah, it's true.
Very useful number to pick.
Yeah, okay. Well, I don't think we quite picked it. I don't know what you're accusing me of. I'm going to say something in passing because I'm not going to come back to it later. But and this was actually hinted at something that was in one of Rajesh's papers that we then showed, which is actually, if I took this log from the outside to the inside for alpha equals 1, then I'd actually get Shannon entropy, specific Shannon entropy on the right-hand side. Okay. So what happened after this? This is 1996. Then there was a sequence of papers, right? So he's assumed that these words are made up of IID letters. Does it really need the IID-ness? Of course not, right? And the question is, how robust is this result? And two very old friends of mine, David Malone and Wayne Sullivan. Wayne was very famous in the 1970s for work on Markov random fields. And Dave you may know because he wrote the O'Reilly book on IPv6. Seems like a strange combination. But they, for instance, showed that if you take Arkan's results and you had Markov, if your words were made up of Markov chains, then everything still holds. Charles and Wayne, Charles Fuster is a well-known, probably also retired mathematical physicist, probably well-known for work on phase transitions. They showed that if you have Sophic shifts that satisfy this like really minimalistic entropy condition, then again everything holds. So it's a really strong result. And Rajesh also contributed to that enterprise by showing again another distinct vast class of processes all have this property. And of course, as opposed to being Riemann entropy appearing, it's a specific Riemann entropy, right? It's the Riemann entropy per character. There's also a curiosity. On the previous slide, I had alpha being bigger than 0, right? Because if I'm thinking of this thing as terms of moments, you only really normally consider alpha greater than 0. Charles and Wayne considered alpha bigger than -1. Charles and Wayne are very fine mathematicians. And I haven't asked them about it, but my suspicion is it's merely because they realize the arguments work for alpha bigger than -1. Can anybody see why it might be important? Right? Come on, Sean, we've been friends long enough by now.
Oh man.
Okay.
Explain, what are the square root of the times?
Alpha goes -1, you get Shannon entropy. If
Sorry?
you let alpha go to -1, you get Shannon entropy.
So if you let beta go towards -1, you get the Shannon, or to -1, yeah,
Yeah.
sure, yeah. Right.
So the Shannon entropy is limiting.
No, so alpha tends towards -1, you get this thing tends towards min entropy, goes off to infinity. Minus min entropy. Okay, so I'm going to be very honest here and explain how this project started. This project started because I had a grad student start, and I wanted to keep them out of my hair. So, you know, it's important that you teach your students these really powerful techniques that you know is going to come in very handy. I'm going to skip through to the next slide. And so we have these results for these moments. And I don't know about you, but I don't often think about asymptotic behavior of moments. I don't really care about it. What I'm really more interested in is knowing something about distribution itself. Right? I want to know how hard it's, you know, what's the likelihood it takes me n guesses. I'm going to mention in passing, and this is why I caught my interest, is that this is really a question about stochastic orders. In some sense, it's nothing to do with guessing for me, in that the probability it takes me n guesses to guess your word is the probability of the nth most likely word. Right? So if I can calculate this distribution or an estimate on it, then what I'm really telling you something about is I'm making these words, and then at each k, I'm sorting them from most likely to least likely, and you're saying, well, what's the nth most likely object in that list? Finding that object can be very hard, but it'll turn out that we'll get a really simple estimate, well, reasonably simple estimate on on its likelihood, which seems surprising to me at least. And so I empowered my student with an incredibly important technique, which is the observation that e to the log x, so long as x is bigger than 0, is x. Right? And so why is that a powerful and important technique in this instance? Well, let's apply that trick to this guesswork to the power of alpha. And if I do that, then what I recognize as this next object along is that it's not really asymptotic moments of this distribution. What it really is a scale cumulant generating function, right? So if you ignore the fact that I'm taking a limit and you take a finite k, the logarithm of this expectation is the Laplace transform of a distribution, right? And it's the Laplace transform of a distribution of the random variable 1 over k log the guesswork. Yeah. So, okay. In the same way that if I gave you a Laplace transform for a distribution, all going well, you should be able to invert it and tell me something about the distribution itself. If I scale these distributions in this way, all going well, I get a large deviation principle for a different process. The different process in this case is kind of interesting. So what their results are really suggestive of is they're really telling you that 1 over k log the guesswork should satisfy a large deviation principle. They're not really looking at the guesswork itself, they're looking at 1 over k log it. And that kind of makes sense. It's a little bit worrying, but it kind of makes sense. So what happens is, as k increases, the number of guesses that you're going to make is blowing through the ceiling, right? It's growing like if your alphabet has n letters in it, and it's growing like n to the k. So by taking a log, I'm trying to manage that explosion. By taking the 1 over k, I keep it all on the page. But it really means we're not really studying the guesswork random variables. We're studying the logarithm. You know? And the reason it's a little bit worrying, of course, is that how much information am I throwing away when I do this transformation? Particularly this log one is kind of quite interesting, right? Because it's non-linear. What it's telling me is that somehow in the scaling, I expect to get a lot of information from my early guesses, and I'm being a little bit sloppier in my later estimate. Maybe that's not completely clear. Anyway, so what it's saying is that if I have this CGF, and I can take its Legendre differential transform. Remember, this CGF is our alpha times the specific Riemann entropy evaluated at 1 plus alpha. And I take its Legendre differential transform, it'll tell me something about the density of this guesswork distribution. But the first thing to note is, of course, I'm taking a Legendre differential transform, so I need to have this SCGF for all alpha. And so far they've only given it to us for alpha bigger than -1. So anybody want to guess? Come on, Ron. You're going to guess what happens to this for alpha less than -1.
Alpha less than 0, you mean?
Sorry, alpha less than -1.
Less than -1.
Less than -1, right? Well, I could ask you to guess, because you should know. So, okay, bit of a mean question, but you know, there's been a lot of bemoaning of the curse of dimensionality. When you're doing guessing stuff and you're trying to hide things, this is the boon of the curse of dimensionality. So actually, what happens is the CGF, which I've already told us about its behavior for alpha bigger than -1, for alpha less than -1, it's just completely flat lines, and it flat lines at minus the min entropy. Minus the min entropy tells you how the likelihood of the most likely word is behaving. Yeah? I think I'm losing people. Oh well. Okay. This is a curious form. Usually scale cumulative generating functions are beautiful curvaceous objects, you know, you want to spend time alone with, kind of thing. But this form might give you cause for concern, right? Because I have this function that's probably very nice and smooth, and it actually is. And then it comes down to something that just goes completely flat. And in fact, there are instances when, so this is just an example with, if I gave you actually a uniform distribution on a binary alphabet, then to the right, this thing turns out to be a straight line. It goes down, and then I have a sharp point where I drop to the min entropy. And that actually is what causes lots of technical difficulties, which why this went from being a 2-week project that I thought would keep my student busy for a while and ended up taking him 6 months or a year or whatever. But I thought I would mention when I got to here something about Riemann entropy in the hope that someone would elucidate me as to whether they've ever seen it before. So I was wondering, we were wondering at the time when we needed it for the proof to figure out this discontinuity in the derivative. What was that encoding? Okay. And so if I take my alpha times my Riemann entropy evaluated at 1 upon 1 plus alpha, and I look at its derivative, and I look at that derivative as I come down to -1, I get some quantity, and the quantity looks like a difference between min entropy and kind of beta squared times the derivative of min entropy, or the derivative of Riemann entropy as the beta is becoming large. And it turns out that this quantity tells you how many most likely words there are. So, in the following sense, if my words were made up of IID letters, it would tell me exactly, basically. So, if I have IID letters, for instance, and one letter is more likely than the others, then the number of most likely words as I make longer and longer words is only going to be one most likely word in each sequence. If I have two letters that are equally likely and are most likely, then of course I'll get an exponential growth in the number of most likely words. And this funky quantity is exactly what captures that. It's embedded in considering Riemann entropes. And the abstract version of it, where you have suffix shifts and the full thing, is also true. What it's really doing is it's saying how many words have you got that their decay rate is smallest, right? So you've got these words that are asymptotically kind of equivalent in that they're they're decaying about as exponentially fast as each other, they're likely, and you have about e to the k times this gamma of them. Okay. I don't know. If anybody's ever seen anything like this before, these sort of manipulations of Riemann entropy, I'd love to hear about it, because we only stumbled on it. Now, it's inappropriate to give a talk with Sean in the audience without touching on Markov chains. So, Markov chains are control, and I don't do control. So I'm going to throw this in. This is for his viewing pleasure. So if you don't like it, you don't like it. It turns out that if you take these words and you make them from Markov chain on a two-state alphabet, then the number of most likely words that you can have, well, it could be that you only have one most likely word, right? That there's a single letter that you want to come back to and so forth. So the growth rate of that most likely word, say how many most likely words have you got, could be e to the 0, there's only one. It could be that both letters are equally likely, basically back to an IID process, and that will give me, the growth rate should be e to the log 2, or e to the k times log 2. And it turns out there's only one other value, and the one other value is the golden ratio. There's no Fibonacci sequence in this, but it turns out the only other thing that you can get is the golden ratio. There you go, just for you, Sean. So that kink, yeah, well, why go into the details? So that kink in that CGF causes of problems. There are standard theorems for which, if you tell me how the scale cumulative generating function behaves, if it's well behaved, I get an LDP. And in fact, most of the standard textbooks tell you should prove large deviation principles that way, and that's wrong. The way you should do it is the way it was originally done by David Ruel and Lanford in the 60s and 70s. And because of that kink in the rate function, we can't use the standard theorems, but we can use the correct way of proving it, which is what a lot of head scratching is. But it turns out basically the thing that they've already established for this class of processes is sufficient to ensure that we can transform the scale cumulative generating function into having a large deviation principle for 1/k logarithm of the guesswork. Right? But I said at the start, I want to know something about the guesswork distribution. I don't really want to know something about 1/k logarithm of the guesswork. Right? So I'm going to tell you a bunch of lies, maybe. So we're going to start with something where I have an LDP for this, 1/k log of the guesswork. I'm going to try and convert it into something about the guesswork distribution itself. What I'm writing here is complete and utter nonsense. You might believe it, but it's nonsense. But you can't make it rigorous, just not by doing it. So, but the nonsense is informative. That's probably not even true. I'm kind of proud of the nonsense. So 1/k logarithm of the guesswork, when k is large, you basically have a density for this guy, right? Because the number of guesses that you could make is growing exponentially. So when I hit 1/k log, I've got this compact interval and I'm really putting in loads and loads of little spaces. So I can almost treat it like it's a density. And then if I was to look at the guesswork divided by just the number of letters, that's also a scaling that gives me something that looks like it should have a density. So I just should be able to look at a continuous transformation and transform the density. I can do that, put in a substitution, and get the guesswork out. The reason why it's complete lies is that none of these things really have densities and so on and so forth. But you can make this approximation explicitly meaningful. The end result of which is, if you give me words of length k, and you ask me, what's the likelihood of the nth most likely word in words of length k, then what I tell you is calculate the specific ring entry, evaluate its Legendre differential transform, and problem. You know you want to, Max. And then the likelihood of the nth most likely word, 1/n, particularly beautiful in a large deviation result. You don't normally get prefactors. You get 1/n, e to the minus k, where k is the number of letters in the word. This Legendre differential transform of that thing evaluated upon 1/k log n. Right? Most natural thing in the world. The thing that's curious about it, I guess, is that as I take longer and longer words, I'm trying to sort, and if I was to actually go and try and sort from most likely to least likely, I have this huge number of words, and you can imagine the complexity is increasing with the word length, whereas this estimate, in principle, is not getting any more complex as k becomes larger, right? As long as you believe that knowing a continuous function, is something I can do happily to arbitrary precision. And I think that's a little curious. Because I'm not telling you what the word is, but I am telling you what its likelihood is. So what does the estimate look like? Here's an example. You have 3 letters, say, words of length 15, so 15 characters, so I've got like 14 million words. The explicit distribution is here in the red line, and the blue line is what my estimate would look like, right? There's fun you can look at if you look at this distribution. It does really nice things. It kind of picks out the most likely word perfectly, typically. And in the IID case, it definitely does. And you can see it gets sloppier as you move further out. It's also, if you, for example, put in a uniform distribution, this is not an estimate, it's correct. If you put it through the mechanics, what this will tell you is that the probability of the nth most likely word is 1 upon m to the k, right? So that it kind of has some naturalness about it. I can't show you on a single graph because, like, on the bottom here, you know, this is like whatever, millions of words at the bottom. So I kind of have to keep some of the original scaling so that you can get a feeling for the convergence of how good the approximation is, right? So this is words of length 10 are the red line, the green line are words of length 20, and the black line are words of length 100, right? And the blue line is my estimate. And they all agree in the first section, and the first section is all of the most likely words. And it gets that absolutely correctly. But as k becomes larger, the estimate becomes better and better, right? These probabilities are infinitesimal at that stage, but the estimate is actually very good. Okay. So that's the first thing I wanted to tell you. And the second thing will be quite brief, but in part because, and this is just for Todd. Todd was commenting on The Economist yesterday. I don't know if this is clear from the back of the room. This is an advert that The Economist ran about a decade ago that my friend David Malone, who was one of the early authors on this Guesswork stuff, took umbrage to, because they had, basically the advert said, if you want to see the big picture, go do something else. If you only want to get lost in the tiny details, read The Economist. All right? So the trees are over there, and the wood is over here on the right, and that's The Economist. So Dave wrote to them and said, you do realise that you've misinterpreted the phrase to be able to see the wood from the trees, right? So that's the phrase in British English, is the wood from the trees, where wood has an ambiguity about whether it's a forest or not, and they misinterpreted it. And they told him, you're an idiot. That's not what it means this. And so what he did is he keeps a web page where he has translations, well, not translations, he has this phrase in hundreds of other languages where the ambiguity doesn't arise, right? And they still tell him he's wrong. But anyway, so up until now, we've been seeing The Economist rather than the trees, right? I got lost in the details. I'm trying to work out this beautiful estimate that I just think is very cute and curious, and was my original motivation. And you know, in fact, this was the only piece of work I've ever sent to transactions on information theory. And I'd heard horror stories about how long it would take to get reviews, and instead I got three very informative, well thought out reviews very, very quickly. And everything was going great, apart from they said, but you know, why are you doing this? And I was tempted to write back and say, well, I had this student in this. but thankfully Muriel saved me, so I'm going to segue briefly into well, could this matter in any shape or form? And as I said, we were talking to Muriel about something else with her student Flavio about list decoding, where again you're kind of trying to hide things in plain sight. And where you're trying to hide them in plain sight is back to the computational security thing. You've got a big long list of things that your object could potentially be. If I have no inclination to know in advance which one it's more likely to be than another, then I kind of try to hide it that way. And the motivation for using a uniform assumption was effectively the asymptotic equipartition property, that if you assume that someone has already done typical set coding for you, then everything should nearly be equally likely, right? So here's my typical set. You give me some epsilon greater than 0, and I take all of the words whose probability is between, you know, Shannon entropy plus an epsilon and Shannon entropy minus an epsilon. And the actual way I would do typical set encoding is I would have some kind of conditional distribution. Right? I pick my words, and if my words end up in this typical set, then they have the likelihood of that word divided by the likelihood of being in the typical set. And if they're not in the typical set, then they have no probability in this conditioned source. And the temptation is to go, okay, well, let's just appeal to the asymptotic equipartition property and instead just say that every word in this typical set has equal likelihood, which is 1 over the number of words in that set. And again, we only entertain this as a brief exercise, expecting to show that in terms of guesswork, so if you now tell me that this is what you've done, you've had some source of words, you've done typical set encoding on it, and now I'm trying to guess, okay, of the thing, I know that your thing is in the typical set, which one, what have you done, what have you selected? We were expecting to show basically that the computational security of each of these things was equivalent, that these kind of small differences in probability in the words wouldn't matter. And that turns out to not be the case. I'm gonna throw up a slide because there'll be a quiz at the end. No. The reason for throwing up this slide is merely to show that. So your original words, like let's say they're made from IID letters, they're very pretty and have nice structure. These new stochastic processes that I make out of them, these typical sets, that they're not IID. I don't even know how you'd nicely classify the kind of distributions you have in here, but basically all of the properties of the original source carry through to the properties that you need for these typical set coded words, even though they're not IID or Markovian or anything like that. And if the original letters were made on a binary alphabet with IID letters, it turns out you can compute everything explicitly. So I'm not going to talk through this, but you get very pretty expressions that I have a funny feeling that if people who are very familiar with information theory would look at and would see connections that I don't see, right? Including these things like where I have kind of a negative divergence plus something times a Shannon entropy and so on and so forth. But the end result of it, and you can do more complicated things, is you can look to see what's the relative hardness of how hard it is to guess should you take this uniform ansatz from your AEP versus the real conditioned process or the unconditioned process. So binary alphabet, if P0 is the probability of me having a 0, then what happens is that there are values of that P0 for which the unconditioned process is harder to guess than the typical set one. That's not surprising because the unconditioned process, I've got a much, much bigger collection of words. That's that lower line. The upper line is the difference between the exponential growth rate of how hard it is on average to guess the uniform ansatz in comparison to the true conditioned process that you've actually put in, and it's always strictly positive. And the reason it's always strictly positive is that it's exponentially harder to guess something picked from that uniform ansatz than the thing you've actually done. So it's kind of a warning that using the AEP to justify a uniform ansatz for asking questions about security might be somewhat dubious. And so I'm going to leave it at that. But basically, we have this bizarre, curious estimate that has some. It's kind of gorgeous and kind of not. And then the final point is really that appealing to the AEP for this guesswork stuff doesn't seem to be appropriate.
Questions?
So have you able to guess out Sean's password?
I suspect it's probably I love coffee. Closer, yeah. Or I love coal, perhaps.
Dan, I have a question.
Sure.
Regarding Rayleigh's entropy with negative alphas. Do you keep the interpretation of the information about from negative alphas?
So, although
You have a function, so you can do anything with a function. But
yeah, I could. So the thing is that I should have been. Let me go back to the expression. So, although they're taking alpha negative towards -1, you're right. So what happens here is that's the equivalent of taking beta off towards infinity. So when I take it lower than -1, I'm going to infinity and beyond.
But what about from 0 to -1?
From 0 to -1.
You keep the concept and information about. I mean, it's just
Yeah.
I think I read his papers, and he says that negative alphas, he could not
You're not allowed.
come out with the concept of mounting information.
Oh yeah, well sure. I mean, yeah, it's not you lose convection. It's
Of
not
course, you
it's
have
not a
function.
nice
You
metric.
have function, right? So you can
Yeah.
continue.
But it's still
right?
yeah.
I don't know, you know, like as I said, it. I think part of the reason we made some progress on it was that I didn't look at this as an information theory problem
Yeah.
at all, right? I mean,
That's what
it's a great question. I really should go read Rini's papers, to be honest. I didn't even do that. I mean, it was. It's just literally a mathematical analogy led us to go off and look. Yeah, but it's a great question. Yeah, but I have very little feeling for for lots of the interpretation of this stuff. As you say, even with the alpha being a half, you know, it's or beta being a half.
But there might be a clue in the slope representing the growth of probability. So I think there might be some interpretation that one could.
There might be, but again, also in the condition thing, when you're conditioning on the typical set, it even suggests. See, Arakin wrote it in this way, looking like a Rini entropy. Because we had to go back through the proofs for other reasons, I would have done something different, personally. Mainly because I probably wouldn't have recognised Rini entropy. But you can actually write it as a difference between a divergence and something to do with a Shannon entropy. And that's really what it feels like to me. It feels like because from a large deviations point of view, that's very much what it feels like. It's telling you how you should trade off tilting something. And the tilt is kind of being determined by a divergence and a difference. So.
In fact, I think the interpretation ought to be that you're actually tilting the distribution and you're compressing the tilted distribution at Shannon entropy. So you're solving a modified compression problem for the tilted distribution, and the penalty is the relative entropy.
Right.
So large deviations is very much at play.
Yeah, and in fact one of those, very much, and I mean it's a curious, you can actually prove it loads of different ways, but like that's why these kind of quantities that are appearing are related to
I think
tilts.
that is actually a scaled entropy of the tilted distribution. So where the tilt is 1 over 1 plus alpha.
By the way, there's also another interpretation, which is that you can consider risk-sensitive version of lossless compression. And when alpha is positive, you actually get standard risk-sensitive version. When alpha is less than 1, you get risk-seeking behavior. And you can actually connect that to some sort of game theoretic viewpoint, because Reni entropy actually arises as a risk-sensitive version of lossless compression.
Yeah, in fact, there is an equivalence between guessing. So with a good guessing strategy, you can essentially get a good code for a risk-sensitive or risk-seeking, either of the. You could get a compression strategy for something where it's e to the L. You're trying to minimize e to be some rho times L or alpha times L.
This one's lossy. It's asymptotically lossy. This one's lossy compression, so it's sort of interesting, right? Usually the two don't.
Where is lossy?
Well, asymptotically.
It's asymptotically.
Asymptotically lossless, yes.
Yeah.
Right.
Okay, well, I guess we should. Thank you very much. We will continue. So,